Okay, good morning. Good morning. Assalamualaikum. Is it better if I use the mic? Okay. Now, yesterday's class, we had done up to this design sequence. Okay, there are 5 design sequence. Okay, to refresh, the 5 design sequence would be first to decide whether the process will be in batch or continuous. Okay, batch or continuous. Then after you decide whether your process batch or continuous, you should identify the input and output structure of the process. What is your raw materials? What is your product? One is for the overall. Each of the unit equipment, what is the input and what is the output? Okay. Next, to identify and define the recycle structure, if it is feasible to be done. Okay, recycle structure. Then identify and design the general structure of separation. General structure before you go into the detailed design. Okay. Then comes the heat exchanger network or process energy recovery. Okay, so now we will go in detail for step by step. Now, step 1. Batch versus continuous. So you should consider which one is more feasible. Okay, more feasible in a way that the reaction is possible to occur. The costing, the maintenance, everything. Okay. The equipment. Okay. The chemical process described as continuous receive their raw material feed and ship their products to and from the plant in transportation. In transportation. Now, the unloading and loading part, of course, will be done in the batch manner. Okay, you need to unload and load your raw materials and products. That one would be batch. If the plants operate continuously, okay, but feed from other process unit within the plant that operate in batch mode, there are mix of continuous and batch. We call that as semi-batch. Okay, the mix with continuous and batch process we call as semi-batch or semi-continuous. Okay, to show that the process is not fully continuous or fully batch. Okay, so I assume by now you should know already how to differentiate batch and continuous process, right? Okay, batch process is quantity of product made during a period of few hours or day. For example, fermentation process. Okay, to produce bioethanol, for example. Fermentation, it required few days or few hours, then only you get the product. Okay, continuous process. Feed is sent continuously to a series of equipment, usually performed in single unit op. Continuous means the feed keeps on flowing and output also keep on flowing. Okay, continuous. Batch feed in, then you need to stop the feed in for a few hours. for the reaction to occur, then only you release the product. That is batch. Okay. Now, there are some factors to consider when deciding whether to do batch or continuous. Okay, these are part of it. Okay, they might be more or they might be less, depends on your process. Okay, based to case basis. Case to case basis. Okay, size, the size of your equipment, your reactor. Product quality. Okay. Then operational flexibility. Standardized equipment. Okay, equipment for multiple products. Efficiency. Which one is more efficient, batch or continuous? Okay. Maintenance and labor. Feedstock availability. For certain feedstock, it is limited. So if you have continuous process, your feedstock need to be ready all the time. If you don't have, if you finish out your feedstock, then you need to stop the process. Okay. Product demand, the rate of reaction, equipment fouling, safety, controllability. This is part of it. Okay, it can be more. Okay, for batch process, suitable if your product requires small quantities, less than 500 tons per year. Okay, this one is in terms of quantities. Again, it should refer back to your reaction and product as well. Okay, variety of different products or variety of different feed material. Most of the process, they opt for continuous process when the product is in large quantities. Okay, greater than this figure. Using a single or only a few raw materials. Okay, in terms of capex, the capital investment, batch system is usually much lower. Okay, and compared to continuous. Because the same equipment can be used for multiple unit op. Okay, but operating labor cost and utility tend to be much higher because for example, fermentation process, you put in all your feed, your raw material, your microbes, then reaction occur over there. In that particular bioreactor, you can collect your biofuel, your gases, product. Okay, but it requires operating labor cost quite high because you need to always maintain the process, whether it is efficient or not. Then after that, you will need to, at certain time, you will need to check whether your target product is meeting your requirement or not, the purity, everything. Okay. Now we move to step 2, the input and output structure. Identify the chemical reaction taking place within the process. Okay, it is to investigate the input and output structure of the process. Input and output for each equipment, for each unit op, and also for the overall process. Okay, input represents feed stream and the output are the product streams or the waste stream. Okay, your effluent. They can be represented in these three methods: the process concept diagram, structure of the PFD, and BFD. Usually, you will start with the BFD first before we go to the process. Okay, BFD. We just draw the box, then reactor, reaction occur, product go to separator. Just use box first before you identify the detailed unit of. Okay, so this is the process concept diagram. Your input, this is the reaction occur to produce your output. Process concept diagram. What is input and output? So, what is the reaction occur to produce your output? Let's say for urea production, your input, hydrogen, nitrogen, reaction occur inside, then urea, your product. Okay. Now, this one, this is the PFD. After you create the process concept diagram just now, the concept, now this shows the process flow diagram. PFD usually more details. Okay, you can see the same input-output structure can be seen in both diagrams. So this is your input, toluene and hydrogen. This is your output. Okay, this is just now from your direction occurs inside to produce your output. Okay, this one just show the raw material and the product. This diagram, it involves the input input involving the utility stream. Okay, where it involves the air, you need the fuel gas for the combustion to occur. Then here you have the waste combustion product. Okay, this is also considered as the output. Whatever product is considered output from your process. Toluene is the input. Okay, this one is clear. Input. The air over here, air and fuel, input as well. But this is the utility. Combustion product is your output. Okay, where this one should be categorized as the waste combustion product. Your main product would be the fuel gas and the benzene. Okay, other than that can be considered as waste. Okay, now this is the generic flow diagram. Actually, before you proceed with the PFD, this one should come first. The raw materials. Then it goes into reactor feed preparation. Okay, the pre-treatment. Then go to reactor. After reactor, you have mixtures of product. Then you will need separator. Okay, this one separator feed preparation. Perhaps here you will need heat exchanger to reduce the temperature so that it can flow in the separator at the set temperature. Okay, perhaps this separator can maintain the temperature at 100 degrees C. But products from the reactor at 200 degrees C. So you need to reduce the temperature first before pass to the separator. Okay. Now from the separator, it will separate the products and byproducts and also the waste stream. This one is the generic. It doesn't mention over here how many separator that you need yet. Okay, the generic one. Once you go to detailed design, then only you should identify how many separator that you need. What type of separator that you need. Depends on your feed condition, whether it is in gas, liquid, or solid. Okay, because gas, liquid, you will need different type of separator. For gas, you cannot use distillation column, right? So you should identify what kind of separator that is suitable for your feed. Okay, clear this one? Any questions so far? Step 1 and step 2? Now still in step 2, feed purity and trace component. Feed stream entering a process do not contain pure chemicals. Okay, if your feed have some impurities, so you should treat that feed first. Perform any suitable pre-treatment method. Okay, there are few steps. We call that as heuristics. Small quantities and inerts do not separate. If it is inert, so it will not contribute to the reaction. It will not affect the reaction. So don't bother to separate because you might need different type of equipment in order to separate the inert, which will involve the cost. Okay. For example, H2 fed to the toluene, HDA process contains a small amount of CH4. But that CH4 does not react. It is an inert, so do not remove. No need to remove. Like for the air, you have O2 and N2. N2 we always consider as inert, right? So no need to separate the N2. Now, if separation impurities is difficult, do not separate. For example, azeotrope, water and ethanol. Why water and ethanol are difficult to separate? Yes, boiling point is too close. Water 100, ethanol 70 to 80 roughly, right? So the boiling point is quite close, so it is hard to separate. If you do the separation, you will require perhaps multi-stage of distillation of few equipments, few steps of equipment. Okay. Now impurities or poison catalyst. That one you need to separate because it might affect your reaction. If impurity react to form difficult to separate, then also separate. If the impurity, if you don't separate later on in the next reaction, it's formed with the chemicals, which is after that the product is difficult to separate. Okay, get I mean? Let's say just now using the CH4, small amount of CH4. Initially small amount, but after that, perhaps after it goes second reactor, it react with another type of chemical and produce product which is difficult to separate. And it will affect your process. So that kind of inert or that kind of impurities should be separated in the beginning. Okay, then if the impurity present in large quantities, then you should purify the feed. Should separate. Okay, then we should consider the stability of the product. If the product stream, let's say a reactive product or unstable, then at certain point you will need to add stabilizing chemicals in order to stabilize the product before it goes to the storage. Okay, before storage. These stabilizing chemicals are additional feed stream, additional input. Perhaps after the separator, you separate and you already purify your product, but it is not stable. So you will need to add in some chemicals to stabilize it before it goes to the storage. Okay, third one, inert to control exothermic or equilibrium reactions. Okay, as in certain process, steam is fed to the reactor to dilute the feed and provide thermal ballast to absorb the heat of reaction and make control easier. Highly exothermic reaction. This one you will need to add in some inert to control the temperature, okay, to control the heat. What is exothermic? Huh? Release heat. Okay, exothermic, release heat. Okay. Now this one should be done in order for you to decide whether to proceed or not with the input and output with that raw material and product that you will be producing. Okay, value of the product minus the cost of raw material. This is in general. For example, urea. What is the cost of urea at current market? Then what is the cost of H2 and N2? Product minus the cost. If you get positive value, then proceed. That means you are making some profit in general. If negative, so don't bother to proceed. You will not get any profit. Okay. Now I explain the theory first. Later, you will look few examples how to implement these steps. Okay, the next step is the recycle structure. Since the raw materials are valuable, unless your raw material is cheap, like you requires oxygen, where you can just get from the air. So that one no need to recycle, right? Okay, but if your raw material like ethylene, you need to buy it. So consider to recycle if you have excess of ethylene. Separation and recycling of unused reactant. Okay, unused. Because in your reactor, perhaps your raw material should be in excess in order for the reaction to occur. So that excess of material should be recycled. The exception is when raw materials are very cheap. For example, the air just now. Okay, and the extent of recycling of unused reactant, it depends on the ease of separation. Okay, let's say your ethylene, unused reactant, ethylene. After reactor, the product stream, you have excess of ethylene plus your product. Then consider first whether it is easier to separate or not. Easy to separate or not between ethylene and your product. If it is easy to separate, then consider for recycle. If it is not easy, difficult to separate, then try not to proceed. Okay. Okay, this one for the unreacted raw materials. Unreacted. Unreacted. Basic recycle structure. Separate and purify. Of course, you need to purify back in order for you to recycle to your feed stream. This one is for feed stream. Recycle feed and product together used as a purge stream. Okay, so this one, if the recycled feed and product together use a purge stream, you need to purge them. Okay. Alternatively, do not use as a purge stream. So either use as purge or not purge them. Okay, that one is for unreacted raw materials. Okay, this one all in the lecture slide. The detail you can read. Okay, as mentioned over here, as recycle stream increase, equipment and operating costs also increase. Because in order to recycle, you will need to separate them first, separate and purify. So it will involve a lot of unit ops where it involves costing. Okay. Like I mentioned in the previous class, from previous PDP on the water issue, because they required highly pure water for the process. But the wastewater that they produce is not let's say, mixed with the impurities, of course, the waste, right? So in order to separate the impurities or to purify the water, they will need some wastewater treatment plant, which involve the cost. Okay, so comparing the cost on the water treatment plant with using fresh water is more feasible compared to treating the wastewater and recycle. So they choose just to release the wastewater, since the wastewater follow the standard. Okay. Okay, these are the few things that you need to consider if you plan to recycle some of your reactants or your waste. Okay, it involves these few considerations. Okay, whether it is any potential for the recycle stream, does it affect the recycle structure? How many reactors or unit op required for the recycle? Whether the stream need to be purified or not. Okay, and all this lah. The next step is the general structure of separation. Now we move to separation. The goal of separation is always to produce a high purity product. Or recycle stream of unreacted feed materials, and to separate the product with streams of byproduct. Okay, your product and your byproduct. How do you determine how many unit op or separators that you require? Okay, so after you obtain your product, you need to consider the minimum number of simple separation unit. Question concerning the separation section. Okay, this kind of question should be asked as well, in order for you to decide on the separation system. What types of unit and how should the unit be sequenced? Separator, it can be distillation column, flash column, scrubber, pressure swing, adsorption. So which type? Distillation only you have few types. Multi-stage. How many stages that you need to consider? Okay. And then adsorption. What is the adsorbent? How high is the adsorption? Do you need microbe inside it? Okay. And then the sequence. If you required few distillation column, how would you sequence it? The top product, the one that should be separated later, or the bottom product that should be the feed to the second distillation column. Okay, later we'll go through on the sequencing part. Okay, this one is the basic step. Remove the largest product stream first. Largest product. If you have, for example, mixtures of product A, B, and C, A, B, and C. A 60%, B 20%, C 20%. So the first sequence should remove the A first, the largest quantity of product first. So your top, let's say top is A, bottom B plus C, right? So that B plus C would be the feed to the second unit of. Now for distillation, remove the product with highest heat of vaporization first, if possible. Okay, the most volatile first. Do not recombine the separated system. Okay, now perhaps you can say it doesn't make sense. After separate, then why need to combine back? But later, if you once you do your PDP, once you run your PFD, then you will see. Because there are certain stream, perhaps you say to save cost or what, just mix them back. Okay. Okay, always do the easy separation first. Do not waste raw materials and do not over purify streams based on their uses. Remove hazardous or corrosive first. Okay, you see there are many statements of first. This one also case by case. Hazardous, between hazardous and more volatile. So you should consider which one to be separated first. There are few considerations. Safety, you consider the safety as well. Now the last one would be use less expensive cruder separation technique first. For example, liquid extraction before the chromatography. Okay, chromatography is one kind of separation technique as well. No, this one is not the sequence yet. This one is the guideline. Guideline for sequencing, the one that we need to consider. Okay, guideline. We don't touch on the sequencing method yet. Okay, just now is guideline for sequencing, for separation. Now this one is guideline for choosing separation unit. Which separation unit to be choose? Distillation or scrubber or PSA? Okay. Gas adsorption. So which one to choose? Distillation should be the first choice for separation of fluids when purity of both products is required, because it depends to the boiling point volatility, so you will get more purity products if you use distillation column. Okay, because if you use multi-stages, then it will be higher purity. Okay. Gas adsorption to remove one trace component from gas stream. Adsorption, remove trace of impurities from gas or liquid stream. Usually this one, for the wastewater treatment, perhaps you need to purify your product. Simpler method is to use adsorption for impurities. Okay. Then consider PSA, pressure swing adsorption, to purify gas stream. Especially when one of the components has a cryogenic boiling point. Okay, membranes to separate gases of cryogenic boiling point and relatively low flow rates. Okay, this one, if you have mixtures of components that have boiling points close or heat of vaporization are very high, consider to distillation. Extraction also can be used to purify a liquid from another liquid. Okay, and crystallization mainly to separate two solids or to purify a solid from a liquid. Okay, crystallization, the product always in solid form. Okay, there are many more over here, up to 16. Evaporation, centrifugation. Okay, these all are the separation system. Screening, float and sink, reverse osmosis, leaching, chromatography. Okay, there are many more that you can consider. Any question on this part? From 1, 2, 3, 4. Huh?
You have to memorize or just understand?
Perhaps you can memorize 5, something like that. No need to memorize all, at least 5. I will not ask question. List all 16 separation system. No lah, no such thing. Okay. Or perhaps I give case study. You will need to purify products that has close boiling point. So what is the suitable separator unit? Okay. Okay, now we move on the last step, which is the heat exchanger network or process energy recovery. Okay, the main objective is always to optimize the energy that a process exchanges with the utilities. Optimize the energy. Because it involves a lot of cost over here. That's why nowadays they move to solar, what else? Fuel cell to optimize the energy. The solar, the wind, the renewable energy. and it affects on the capital investment. Okay. The utility usage can be decreased by exchanging energy between the process stream. Okay, energy integration effect on the cost. Okay, it's all about the cost. Or the process may become more complex and more difficult to control. So this loss in flexibility must be weighed against the saving of the cost. Okay, basically, for the heat integration, energy recovery mainly focus on to optimize the energy and to reduce the cost. Okay, for example, over here we have heat integration. This diagram, you have stream in, input, output. The input should be 250. Perhaps maybe due to the setting temperature inside this reactor. Okay, 250, and the output temperature is 364. So the stream from the previous unit op is at this temperature. So this stream need to be heat up to 250. So to heat up the stream, you will need HPS. What is HPS? High pressure steam. Okay, so heat up using high pressure steam to 250. Then the output temperature need to be cooled down up to 100 using CW. What is CW? Cooling water. Okay, cooling water, chill water. Now this is before the heat integration, without heat integration. Then we do the heat integration where the output of the reactor, output temperature is already high, 364. Okay, so we direct this stream into the heat exchanger network, where this heat will heat up the input stream. It will heat up the input stream to 250. And this output stream will be cooled down at the same time. Okay, so here, to heat up the stream, in the heat integration part, you don't need the high pressure steam anymore. Okay, we reduce the utilities. We don't need the high pressure steam over here. Okay, and we just need chill water to reduce the temperature of the output stream. But here from 270 to 100, the difference is quite low. So you will require low energy to chill, to cool the stream. Okay. Last time during your secondary school, every week you should wash your school shoes, right? Did you wash your school shoes every week? No, every 2 weeks or not? Then wash at all. Okay, if you wash, let's say that particular weekend is rainy weekend and your shoes cannot dry. What you do? Ah, no need to wash. Let it. Okay. What you do to dry the shoes? Fan. Use fan. Put in front of the fan. Other than that? Huh? If it is rainy weekend, no sunlight.
Hair dryer.
Hair dryer. Okay. What another method? Other than that? Behind the fridge. Okay. You see, if you use fan or hair dryer, you generate the utility consumption. Right. But if you put behind the fridge, no utility, no new utility consumed. Right? So that is part of, that is one concept of heat integration. You use the heat produced by the fridge to dry your shoe. So no utility, no additional utility over there. Okay, understand the concept? Huh? Now this example of another heat exchanger network where they use the streams to cool down another stream or to heat up another stream. Okay, for example, we have here C2 from 180 Fahrenheit. You need to heat up to 232. Sorry, you need to heat up to 240. Okay, but in the process, you have a stream at high temperature. H1, hot stream. Cold stream. Okay, hot stream. So this hot stream you can use to heat up this cold stream, the C2 stream. Heat up to a certain temperature. But if it still doesn't meet your required temperature, you will need to supply some steam. So this steam, perhaps it use lower energy compared to if you don't have this heat integration stream. Okay, can you understand? So we do heat integration to reduce the utility consumption.
Because the temperature difference not too much, it's fine for us to not connect.
Connect, yeah, integrate.
But the shrimping and high yield temperature here.
Yeah. If let's say C2, you need to heat up, right? So before heat integration, you will need to put steam at high energy, at high amount of steam in order to cool up to 240. But if you have another hot stream, which is coming out for another process, so you can heat up this particular stream to a certain number of temperature. It depends to the temperature change as well. Okay. So it will increase some lah. Or sometimes the heat stream can increase up to your desired temperature. It depends to the temperature of the stream as well. In Dr. Ng in part later on, you will learn how to calculate it. Okay. Okay, the boxes over here is the heat integration part. Heating and cooling. Now this one is the onion model. It starts with the reactor. This onion model starts with the reactor. Because the process most of the time will involve reaction and it needs reactor. Right. In order to get your product, there might always have reaction in order to produce your product. So you need reactor over there. Now you first layer inside out, the reactor start first. Process design start with the reactor. In your urea production, you will need to consider reactor because have reaction over there, right? Input, output. Then once the reactor is decided, design the separation system. Your product has mixtures of product. Then consider the separator system. Next one, establish the material and energy balance. After that, hence, you can proceed with the heat exchanger network. Okay, because once you identify the reactor, the product, and the separator that you should use, then you can proceed with the material and energy balance to analyze on the heat exchanger network. What are the temperature in your product stream? What is the feed required into your reactor? Okay. The fourth layer comes the utilities. Okay, after utility, you should analyze on your waste. What is your water and effluent that you are producing? Whether it needs another waste treatment plant or not. Okay. PDP now, you have to do waste treatment plus heat integration, both. Previous semester, they can choose either one. This round, you need to do both. Because you need also to know how to deal with your waste, how to manage your waste. And at the same time, you should know the heat exchanger network for the energy recovery. Both are important. Okay, we try this example. There are two viable routes to the production of hydrocarbon solvent S. Solvent S, so liquid or gas? Liquid, right? Starting with feed material A is your feed. Okay, route 1 uses a disproportionation reaction, route 1, which the feed material A is converted to S and R. Both are solvent. Notice it is in liquid form. Okay, the phase is liquid. So route 1, this is the reaction involved. S and R both are marketable product. Then route 2 start with the same chemical A but uses hydrodealkylation reaction to produce the desired solvent. Okay, so this one. Now your main product is what? Main product, S. S is your main product. The rest are byproduct. Okay, assuming that pure A is fed to the process, pure A. Solvent S and R are separable by simple distillation. and both are much less volatile. Either much less volatile than methane and hydrogen. Less volatile. Okay, less volatile than methane or hydrogen. Here, CH4 and H2. In route 2, there might be hydrogen in the stream as well. Excess of reactant. Okay, there are possibilities. Okay, now the question asks you to sketch PFDs for route 1 and 2. I would say sketch the BFD lah, BFD, not PFD, BFD, block flow diagram. Now we do it together. Wait, Okay, this one is BFD, BFD, block flow diagram. Now we try to sketch for route 1 first. Route 1. You will have reactor. What is your feed? A. Product S and R. S plus R. What is the phase? Phase of S and R, the phase. Liquid, right? Liquid. Okay, both liquid. Both liquid, huh? Yeah. So here from the statement, it mentioned S and R are separable by simple distillation. So after the output from the reactor, to separate S and R, we can use simple distillation. Okay, route 1 up to there, we already get our S, the main product solvent, solvent S. Okay, any question for route 1? Clear? Now, for route 2, for the reactor input, what is the input? A plus H. Can? Yes, can. Yeah, we'll do 2 arrows, easier. Okay, reactor, you have A and H. Now, your product stream you have S, you have CH4, perhaps you will have H2. Okay, even though it doesn't mention H2 is excess or not, so we try to assume, because here it mentioned, because have this statement, S and R less volatile than methane or hydrogen. Okay, let's say we assume got H2 over here. Now, S is in what phase? Huh? Liquid. Methane?
Yes.
Gas. Hydrogen? Gas as well. So you have mixture of products with multiple phase, liquid and gas. Okay, for the separator, what you should use? This one should focus on vapor liquid separator. Okay, so you can use flash drum. For example, flash drum. So you will have your S and the gas. CH4 plus H2. Okay, so now you have your S. The H2 you can consider or not consider in your product stream. It depends, up to your justification. Okay, okay, we just stop up to this vapor liquid separator since we already get our solvent. Okay, okay. Now, route 1 and route 2, we have reactor and separator. But the difference is on the separator. Different type of separator, right? Okay, question 1 answered. You only need to sketch the BFD. Now, question 2, it asks you which process do you think will be more profitable? Explain your reasoning and assumption. 1. Because
They require high temperature. Price is more. But it's like problem with the atmospheric and also the boiling point rate difference is quite big.
yeah, acceptable. Any other justification? Again? Byproduct in route 2 can be sold. Correct? Okay, profitable here, not necessary to focus on the cost of equipment only. Perhaps for route 2, you produce byproduct methane, which can be sold. Okay, and route 1, byproduct is R. In the statement over here, it mentioned marketable products. Okay, you have also, you can sell R as well. Okay, so in question 2, it depends to your justification. Okay, there is no right or wrong. It depends to your justification. Let's say simple distillation over here, perhaps you require specific materials, then the cost will be higher. Okay, so it depends on how you justify. Yes.
Should you answer should I answer still depend on the situation or assume this one is a bad?
Yes.
So just say assume.
Yes, depend on your assumption. So there is no right or wrong for question 2. Let's say you say route 1 is more profitable because only simple distillation will be used and cancel R. Byproduct R can be cell. Okay. And then another student said route 2 because use vapor liquid separator, flash drum, perhaps lower cost compared to simple distillation, and can sell the byproduct as well, stage 4. Okay, I will look on your justification. Okay, there is no one specific answer. It depends to your justification. Okay, then okay, this actually I put example for this one is vapor liquid separator. Wait, I make it bigger. Okay, this is vapor liquid separator. And this one is simple distillation. So simple distillation, no stages involved, simple distillation. But it requires the condenser and the reboiler. Okay, vapor liquid separator, you will need this kind of equipment. Okay, this kind of unit op, where you need, the concept would be to separate the liquid down here and the vapor, how to capture the vapor. Okay. Yeah. Any questions so far? Okay. Try to do example 2. In example 2, you are given DME. The product is DME. Can be produced by dehydration reaction of methanol using solid catalyst. Your input is methanol. Conversion of mixed feed stream of methanol and ethanol via dehydration reaction are given as follows. Okay, so there are this reaction, input is methanol. From methanol, you get your DME. Okay, using ethanol, you will produce diethyl ether. Diethyl ether. Okay, so the stream leaving the reactor, the output of the reactor, contains the following components. Okay, it has this mixture. Here it already listed in order of decreasing volatility, decreasing. Okay, if the conversion of methanol is given as 75% in reaction 1, while 68% of the ethanol is reacted in reaction 2 and 3. Okay, illustrate and explain. 2 alternative preliminary process flow diagram. Assume all compounds behave ideally, and there is no formation of azeotropic mixture. Okay, there's one hint over here. Recycle stream are normally incorporated in process follow diagram, the PFD, to recover the unreacted reactants. So that means over here, the unreacted reactants will be recycled to the feed stream. Okay, try to do this. Make sure you try. We will discuss in our next class. Okay. Okay, before I stop the class, any question? Next class, we will discuss this example and we will do few test and final exam questions. Okay, so that you can understand more. Huh? Next class. Next class? Thursday, right? Thursday. I don't take one. I will record the question. Okay, that's all. Thank you.